visually is 3. Okay, the next node we see is A. Now, A actually has 2 predecessors. We backtrack, we can see that A goes to S and A goes to B. So we get S of 0 plus the weight of weight from 0 to A, S to A, equals 0 plus 6 equals 6. But we also have S of 0 plus the weight of S. Now we've got to be careful. The parent is B. So it's S of B, because this node is backtracking. Let me do this in blue again. The parent of A from here is B. So we're going to S of B plus the weight of B to A, which is equal to the weight of it is 3 plus 2. Oops, do that in black. Was equal plus W of B to A equaling 3 plus 2 equaling 5. And you can see here that this guy wins out. So S of B is 5. So S of A, sorry, is 5. And its parent is A. Notice you go to B, sorry. B. So this is telling you you go to B, parent B, and then from B you go to A. And you can see we have to backtrack at each step. We're kind of running out of space in this because I'm trying to do it very carefully. So the next one is D. So we're looking at D. We get D backtracks to B, and it also backtracks to A. So let's do S of A plus the weight of A to D. That's equal to S of A. That was 5. I should have written that in. There's 5. Plus A to D is 2 equals 7. We also got S, and parent of D is also B. So we get S of B plus W of B to D equals S of B is 3, and B to D, which I've got erased, is 5. And that's equal to 8. So if we go to B, it's 3, then 5, it's 8. So in fact, this is the smaller of the two. Maybe what I should do, just get red out. It's this one, and then this one. So I just mark that one. So the parent of D is going to be A, and the distance is 7. How's it going? Has everybody got the idea? Checks? All fairly simple? Because I'll move on to the next question. So, okay, I'll move on to the next question. When I post the solutions, I'll finish this off, but it's fairly simple what's going on. The next one would be C. And we can do C, and C has backtrack to D and to A. So S of A plus the weight of A to C, or S of D. plus the weight of D to C. And we can keep continuing just like that. All right, actually, we might as well do this one since we got this far. It's equal to S of A. By the way, D was 7. Write that in. S of A is 5 plus the weight from A. How do we get C? Going to D. D is going to S. So S, this is S of D. Okay, plus the weight D. So C, we backtrack to D. So S of D is 7. Plus the weight of D to C is 2, equaling 9. And this guy, this is the distance. To S. And from S to C. There we go. So we're going from S to C directly. So we're staying at 0. So this is 0. We're at the root. We don't go anywhere. And S to A is 10. It still gives this guy as the minimum. So that tells us that to get to C, the distance is 9 and the parent is D. And from there, we can, I'll leave it. I'll have this written up tonight. Okay, so it's a fairly simple question. And then you can draw the tree. Very simple. How you draw the tree, you look at the parents. S is the parent of B, so we get S to B. We can't exactly draw it till we get the whole thing finished off. All right. Let's move on to the next one. Okay, famous knapsack problem. Good possibility we'll have a knapsack problem on the final. Let me just bring over, just for a second, I wrote the code to give you the answer. That's just using a function I've written in MATLAB. It's identical to how we write it by hand, and it quite quickly gives you the solution. So the code for that I can show you a little bit later. But what do we do? The first one, the weight is 4. So that means 1, 2, 3, 4 is the dividing line. And we can put nothing up to 4. Then after 4, I can put 1, the value 18. So the first item is 4 pounds. So if your knapsack is less than 4 pounds, I can't carry it. But if it's more than 4 pounds, I can carry the first item. All right. The next item is 5. All right. So what we have to do is to do a shift, and then from there, sorry, next item is 3, staring at it. So we have to do a shift of 3. 1, 2, 3 to create space. So that's creating space.
Professor, that is a 5.
Say that again?
Like the weight is 5, not 3.
The weight is 5 over there.
It is 5?
Yeah, it's so the one you circled there, it's 5. So it's
Hang on.
item 2, weight 5, and then value 21.
Yeah, hang on. I'll just check if my answer is correct before I continue. The weight is 5. Yes, 4, 5. You're right. So I have to create space for it. 4, 5. So that's the space. And then I take the previous line and I add. So the previous line I have to do the shift, which is 1, oops, black. I have to put a shift in 1, 2, 3, 4, 1, 2, 3, 4, and then I put in 18, 18, 18, because I've created space for the item, and then I've got to shift the remaining one. This has got to be shifted by the 4 that I've created space for. Okay, we now add the 21, kicking in at 5. So this is still going to be 0, this could be 0, this could be 0, this could be 0, and that's going to be 0. But at 5, I can now put in 21. It's 21, 21, 21. But now I get 39, 39, 39. All right, so I've created space so I can add the second item. So here I come add in the second item. Oh, very good. Second. And I can add it in at this point after 5. So I get 21. Here we've got 18 in a knapsack, so that makes 39, 39, 39. And now what we do is we look at these two and compare them and put the max in. So this could be 0, 0, 0, 0, 18. We get 18 there. We get 21 here. We get lots of 21s. 21, 21, 21. But here we kick in with 39, 39, 39. How's it going so far? Yeah. Let's look at the third item. Third item weighs 2. So I'm going to put 2 in. So I'm going to create space for the third item. Now I have to do a shift. So I take this bottom row here, 1, 2, 3, 4 zeros, and then an 18, a 21, a 21, 1, 2, 3, 4, 1, 2, 3, 4, and finally a 39, a particularly messy 21, 21, 21. So as before, we have to shift by 2, and now the third item has value 9, so we start adding 9 in, 9, 9, 9, 9, 27, 30, 30, 30, 30, and then 48. And now, as usual, we compare this row with this row. All right. And choose which one's the max. So we're going to get 0, 0, 9. Just check my goodies. I get 2 9s, 2 9s, yeah, 2 9s. Why am I getting 0, 0? A bit lost. 0, 0, 0, 0, 0, 0, 1, 2. Anyway, we keep going. 0, 0, 9, 9, 18, because that's the maximum. 21, but now we get 27, we get 30, we get 30, but here we get 39, 39, and finally we get 48. All right, how are we doing? Yes, everybody okay? Any checks? Anybody saying? Yes, we're doing okay. All right, so it's a fairly simple algorithm, as I think you can see. All right, I'm just checking who's here. Hang on. Click the page. Pull this down a little bit. So I've got all the students here. All right, so we'll keep going. It looks good. I'm just wondering about my program. I'll be 45236. 45236. V 18, 21, 9, 14. All right, well, I'll keep going. So the next item, 2 more to go. Next item is 3. So I put a reserve space of 3. I can put that item in. I shift the previous line by 3. So this is going to be 0, 0, 9, 9, 18, 21, 27, 30, and 30. I now can add the 14 in. So 0, 0, 0. After 3, I've created space for it. So now I can put the 14 in. 14 in. This one will be 23. And if you think about it, this item is 4. This item is 3. Not quite sure where 23 is coming from. 19, 9. So the 9 is 2. '23. So we get 36, 48. Nope, we're adding 9. We'll get this right. The value is 14. So we're adding 14 to the previous line. Oh, 23. 14 makes 32, 35, 41, 44, and 44. Let's look at the max. As per usual, we get 0, 0, 0. Oops, sorry, 9. 9 there. Then we're getting 14. Then we're getting 18. Then we're getting 23. Then we're getting 27, 32, 35, 41, 44, about 48 here. All right. Okay, so 41, 44, 48. Yep, 35. All right. Last item is 6, the biggie. So 1, 2, 3, 4, 5, 6. There's the space we've created for the 6. So this is 0, 0, 0, 0, 0, 0. Created a space. Got a shift. 0, 0, 9, 14, 18, and 23. But now 6 is 27, so 0, 0, 0, 0, 0, 0. And now we can add 27. 27. Here we get 36. Here we get 41. Yep, I think 41. Right, 27 and 14 make 41. 27, 47, 45. And the last one, 21, 44. So let's have a look. 27.
That last one, I believe, should be 50.
Yes, you're right. I can't add 23 and 27, even though the answer is looking at me. All right, let's go. This is it. The last line. 0, 0, 9, 14, 18, 23, 27, it's a tie, 32, 36, 41's a tie. It's very interesting, we've got ties, 45 and 50. Okay, so the winner is 50. So coming back, the max value is 50. However, what they don't do in the book, but what we do, is actually finding items that gave you the 50. So let's go ahead. What we do is we go to 48, I'll do it in green, and we see it's different. Therefore, we use the last item. So by using the last item, I have to go 1, 2, 3, 4, 5, 6. So I go 6 across. I used the last item. So this got used. I'll circle it. And we have to go 6 across because the last item is 6. Then we look at 27 and 27. It's the same. So we didn't use that item. It says. Confusing. 27, 23, 27. Yeah, so we didn't use that item. What was item 4 weight? The item 4 weight value is 14 weight 3. Anyway, go up to the next item, and we can see that 27 to 21 does get used, and that item.
I have a quick question. I thought once you go up, go left 6 spots.
Yeah, I my mistake.
Yeah.
Yeah, it's this one. 21. Okay, so it takes us back to 21. There we are. We're here to here. And yes, that is different. So we got the second item. Okay, so we got 2. But 21 to 21 doesn't change. So we didn't use the third item. All right. So let's see, hang on. We did use this item. Moved up 23, 1.366, 21, we did use it. So the fourth item weighs 2, 3. The fourth item was 3, so 1, 2, 3. There we go. So if I circle, then I got to move. So this circle I had to move 6. This circle I had to move 3. So it takes me to 9. Up to 0. That's different. So I did use the third item. The third item weighs 2. So I have to shift over to 2. 2, I go up to 0. That's no change. And 0 to 0, that's no change. So the answer is the 3 changes we get are 5, because we got the change, the 4, because we got the change, we got the 3. So it's 3, 4, and 5. What is the value if it's 9 and only the first item's going to be used? Let's do this in orange. So you've only got the first 4 items, so we're kicking in here, and we're kicking in here. So 4 items and 9 gives us 41. Yeah, so it's 41. Okay, now the problem with the backtracking is I can only do that by keeping the whole table in storage. And as you can see, the table is 3 times 5 items is 15 rows. And the number of columns is 12. So that's, if you've got a big data set, that's using a lot of storage. I can't think offhand how you can simplify it that much. I think I can ignore a whole bunch of values, but I only get half. I might be able to get it down to half the storage, but nonetheless, it's still a lot of storage. So I don't know if dynamically I can. It looks like we have to get to the 50, and then we go up 1, and then we go over. So I'm going to have to think about how we can do this. Maybe it's going to require some thought, but I'm sure it can be done. All right, let's have a look at this one. This one's a biggie. Let's get it slightly smaller. How are we doing for time? Oh, pretty good. We're halfway through. This one has, all these questions have high potential for being on the final, but I'll be quite honest, asking all of them, I'm not quite sure we got room for asking all of them. Anyway, we're looking at trying to decide what's going on. And as I say, it doesn't hurt that we're going to include initially this guy, because it's a root, this guy is a root, this guy is a root, and it's going to be 1 plus the grandchild is 1, and the children isn't any. So we get 1, 0, 1, 0, 1, 0, and of course we can put this is L, M, and P, so children we don't have any. 1 plus no grandchildren. L is going to be 1, 1, 1, and S is going to be 1, 1, 1. S, remember, is counting if you include or not include, and that is dependent on G. So if G is being counted, you put 1 for S. So this is equal to G. It's giving you, yes, I'm including you. So we get that. Now we move on. Let's take a nice green color. We're looking at K. Oops, well. We're looking at K, and if we count 1 plus the grandchildren, I get just 1, because there are no grandchildren. On the other hand, if I count the children, there's 3 of them. So we're going with the children, and therefore we're not going to circle you. Since 3 children is the max here, I get 3 children. There it is, 3. But I only get the 1 here because I got no grandchildren. Therefore, L becomes 3, is the max between these 2. And I'm not counting you. How's that? Everybody okay with that? Yeah. A check mark? Someone okay? Yep. Thanks, Maxwell. All right. Next one's J. J, if I count 1 plus the grandchildren, I get 4. 1 plus the 3 grandchildren give me 4. If I count the children, there's only 1 child, and it's 3. Okay, so here we've got 3 children. See, the child is K, and it has value 3. And we put the value of the child, the value of the grandchildren. So that's 3. 1 plus G is 4. We like that. So we're going to go ahead and do 4. And we're going to count you. Okay. Next move on to I. So I, 1 plus the grandchildren. The grandchild is 3. Only 1 grandchild of I, it's 3, so we get 4. On the other hand, if we're looking at the children, it's also 4. It's a tie. So what we have is 4 either way. I said if it's a tie, don't count. So don't count. Do this. Okay, so we got the 3 here.
Professor?
Yeah, 4 here. I said don't count. So don't count it. Yep, question?
Yeah, why are we not counting it? What is the
Because
S?
we've already circled J. So what's going to happen if you circle it? We got I and we got J both circled. It can't happen. So one of them would have to be deleted. Might as well delete the parent. It could be either one, but if I want to delete J, I have to go back and delete it. Whereas if I want to keep J, I have to make sure that I don't circle I. So got the idea, you got a tie, 4-4. So it doesn't matter which one we're going to go with. We're going to go with not including you because, as I said, if you circle I, you've got to go backtrack. And if you backtrack, you get rid of J, but it's no big deal. So I'll leave I. I'll do it that way. One has to go. Yes? If you circle I, one would have to go. Because if you can't have IJ both circled.
Okay.
Yeah. So since we're, it's dynamic programming, we'll choose I to be the one we're not going to circle. All right, move on. We've got F. F is 1 plus a single grandchild, so we get 5. Oops, make it black. So this is 5. It didn't make it black either. 5. And that's looking horrible. 5. And then we're looking at the children, that's 4. So obviously 5 wins out. Therefore, we're going to circle F. So we're going to get F is over here. And we got, it's 5. Children is 4. 1 plus G is 5. So we're going to get 5. And we're going to count you. Okay, so far so good. I think it's a little bit bigger. Yeah. Squeeze it up a little bit. There we go. All right, the next one on the list, that was F. B, 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 B. Actually, we should be doing it going because this was redraw the map. Didn't do the ordering. Okay, so the next one on my list is G. Now, in fact, I could have done H, G. I should be following this list going backwards, but I didn't. Anyway, H is a node. So it's, I did it already. Then we got G is a node. I did it already. So when you got a node, it's 1, 0, 1, 0. And so G is 1, sorry, 0, 1, 1, and I'm counting you. And H, I got that one in, and we got G. All right, so now let's have a look at E. E was back here, so if I was doing it in order, which on the computer we have to do, but we don't do. So let's have a look at E. E is 1 plus the children, so we get 1. 1 plus the grandchildren, we get 1. If I count the 2 children, I get 2. So in this case, the children win out. So E, wherever E is, there it is. E would have 2 children. 1 plus the grandchildren is 0. So L is 2, and we're not counting you. So we're not counting you. All right. So if I'm doing this correctly, H was a node. Let me see. Yeah, so that's 1, 0, 1, 0. E was 1, 2. L was 1, 0. M was 1, 0. P was 1, 0. K was 1, 3. J was 4, 3. And I was 4, 4. So the next one on the list is F, and that was 5, 4. So now we got D. If I'm going off right to left, we got D. Here's D. 1 plus the grandchildren. Now let's have a look. D's grandchildren are H, G, and I. So we get 1 plus 1 plus 1 is 3 plus 4 gives me 7. So 1 plus the grandchildren is 7. Go over that again. 1 plus 1 for H, 1 for G, 4 for I. So that makes 7. Let's have a look at the children. We get 2 and 5. What's interesting, it's the same. So we get 7. As usual, I say, don't circle you. So we don't circle you. All right. Okay. Yeah, let's keep going. The next one would be, so D was 7, 7. The next one is B. We actually don't need them in this list, but I put them in. The next one is B. There it is, B. So we come to B. 1 plus the grandchildren. Grandchildren are E and F, which is 2 plus 5 is 7. So this is 8. And add up the children, it's only one child, is 7. So the winner is 8 over 7. So that's 8 over 7. Running it in. So D was 7, 7. L is 7. And S is 0. I said make it 0. B is 8. So let's have a look. Grandchildren was 8. Children is, oops, wrong one. So C, we'll look at B. So B is 7, 8. L is 8, and we are counting you. 1. C is just a classic node, so we already know that that's 1, 0. So C is 1. Children, 1, 1, 1. And lastly, we got A. And A is 1 plus a grandchild. That gives me 8. Or I add up the children, and that gives me 7 or 8. Let me see. So 7 and 1 make 8. I get a tie. Oh, by the way, this looks a horrible mess. So this is 1, 0. I go with 1. Therefore, I color you. I go with 8. And as I said, we don't color you because if I color you, then I have to uncolor the children. So we don't color you. So someone could do this in a slightly different way, and they would might end up, if you resolve ties by including, then you might get a slightly different picture. All right. So let me write these down. 8, 7, and 8, 8. It's interesting. So the max independent set is 8, and we can see it 1, 2, 3, 4, 5, 6. And we included J. I forgot to circle J. So 1, 2, 3, 4, 5, 6, 7, 8. There's the picture. And now we just have to check that no child is included. Well, we carefully constructed this so that we don't have, in this particular graph, 2 reds next to one another. If we had included those roots, in other words, we had the choice here, doing orange, we had a choice here, then we would, if we put that in, we had included that, then when we're going left to right, F would have to be discarded. Then you would have to discard F. So had we have included I, then we would have to choose discard F. It gives a slightly different picture, but it's still 8, of course. Nothing's changed. We got one of those two. Similarly, here's a situation, and here's a situation. So yes, we could include, for example, had we included this one, we would have had to exclude that one. And the root, I guess. And exclude that one, include that, but we would have included D. We would have been able to have the option of including D. So as I said, you get the same result, but it's better to not include the tie. So this usually goes to that we don't have any 2 red edges together. So A was 8, 8, 8, no. Okay, so A was no, B was yes, C was yes. We're going to get the same answer as above, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1. So that's it. That's the whole picture. And it gives us very, and again, I've got a program, does it instantaneously. Well, All I have to do, I'll show you the program over here. Coming up. So all I have to do in the program is just list the edges along with the weight. There we are. So this would be 1 to 2, A, B, C, A, B, C. I just like numbers. So we got 1 to 2, 1 to 3, 2 goes to 4. So it looks like it's pretty much the same tree. It's slightly different, but there's the code. And it runs pretty much the same code as I've written down. I don't know where the code is. Max independent set. So I have to find you the code. So I'll actually run this so I can put its picture on. Let me do file. Open. What are we looking for? Max independent set. Ah, I can't find it. There we go. Found it. There it is. So here's the max independent set I wrote. And as you can see, right here, I say if C is less than or equal. So if C is equal to 1 plus G, so there's the tie. In this code, I let L be 1 plus G. Now, I could have put C in. It would have been the same thing, but at the end, I have to go through and exclude the ones where we got the children are the same color as the parent. It's right here. I have to include the children. Okay. So by excluding the ties, I think, I'm not going to guarantee it because I haven't done the proof yet, but I think if I always exclude the child, the tie, so I exclude the child and only go with 1 plus the grandchild. Sorry, if I exclude the 1 plus grandchild and only go with the child, I don't get any double red. Now, I haven't proved that yet, and I haven't seen it in any textbooks, so I'll have to go back. But it seems to work. With all the examples I've done, it seems to work. All right. What's the bound for doing this? Well, we're doing each edge, right? So we're doing each vertex and each vertex. Now, how do we get the runtime? It's a good question. How do I do the runtime? Anybody got any thoughts of how I do the runtime? Well, I'll explain. Each vertex can only appear twice. It can appear as a child, or it can appear as a grandchild. So each vertex can only show up in two steps, one being a child and one being a grandchild, sort of. I think, is that right? So it limits the number of times it can show up. It can't be this one. It can't be that one. It's not O of V squared. O of V. It could very well be O of V. It's O of V, because I said, if you look at it from the point of view of being a child or a grandchild, it can only be a grandchild of one node. Look, here I am. I backtrack. I'm only the grandchild of F. Backtrack G. I'm only the grandchild of D. So each node can be the child once, or it can be the grandchild once. So we get 2 times V. And 2 times V is O of V. All right. Last one. How are we doing for time? Oh, not too bad. We're almost going to be done. All right. Here's where we got the current. And what we've got is, if I take orange, this guy is not in the heap anymore. Notice it's -1. It's no longer in the heap. Look, S has been processed. And this guy is not in the heap anymore. So we've only got 4 nodes in the heap. And there they are. B is at the top of the heap. Its 2 children are Z and E. And then Z has 1 grandchild, D. Now, I should give space to put in the values. And though, so if we're doing a slightly bigger picture, D and E and B, I can also go ahead and put in now B has value 6, I use red. So B is value 6. Z is infinity. In fact, everybody's infinity. So that's what my heap looks like. Everybody okay? Or we got, just reading off, H is B, Z, E, D. And if I look at the distances, I get 6, infinity, infinity, infinity. Yeah, and it looks like a min heap. Now, what we need to do is, look, we're looking at child D. So the neighbor of C is D, neighbor of D. We're going to the actual.
I had a quick question on this. So it looked like in, I thought the neighbors were supposed to be B, D, and E. Because B hasn't been a visitor or anything like that.
Well, we're looking at, we're looking at B. So the neighbors are C. C has just been deleted. Look, it tells you here that C has just been deleted. So C has been.
I get that. But if you look at C's neighbors in the graph, it's not just D and E. It's B, D, and it's A, B, D, and E. But
Yeah.
A's been visited, so B should be.
Yeah, so A has been processed, so you can't do A. And so we got B and E. You're right. That's a mistake. Yeah. A,
Like a
B. Oh,
D and E.
hang on. I see. It's a mistake. I hope everybody, I was trying to be helpful. Sometimes when I'm trying to be helpful, neighbors of C, this is wrong. All right. Oh. Yeah. Yeah. Okay, you're right. The neighbors of D are A, B, and D and E. So I missed B. Is that what I done? B has not been processed. That's right. Okay. So A is out of the picture, but B, D, E are in the picture. B, D, and E. So I missed B. All right. So I should have put B in there. Execute the next two updates. We'll do B. Oops. Okay, so with that, update B. So updating B, and we're doing Dijkstra's algorithm. Just make sure that we know what we're doing. So we're updating B. So what we've just done C, so we have to look at the current value, distance B, according to this is 6. Distance of C plus the weight of C to B is, distance to C is 2 plus 3 equals 5. So update distance of B to 5 parent of B is equal to C. So we're going to make those changes in our graph. So B is going to change to 5. And nothing needs to be changed because it's still a min heap. No change. All right. So we could keep going. I know what this is. It's just left over. So the next one, so let's update this. So this one, we changed B's parent to C. I'll do it in red just to emphasize the changes that we made. This now becomes C. Its distance is 5, but its position stays 1 because we're not altering its position. So the others, we've made no change. So D, E, E, we still have no parent for them. And distances are infinity. Oops, no change. Oh. Infinity, 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 and positions are exactly the same. No change for this. Draw 3 and 2. Yeah. All right. So let's do the same. So no change here. No change here. This is still B, Z, E, D. Because there's no change. This meant no change. 5, nothing happened. You only changed to 1 at the top. All right, so let's do the next one. The next one, really, I'm just going to do it. I've left space for it down here, but I'll just do it again. Okay, the next one is that we get, that was B. So now we do update D. Okay. So the distance to D is infinity. The distance to C plus the weight of C to D. The distance to C was, we had it before, distance to C is 2, plus the weight of C to D. The weight of C to D is 2, equals 4. So we went out with that. So we're going to update distance D becomes 4, and the parent of D equals 5. So now what's going to happen to my heap? So there was no change here. So let me just write this in. There was no change. We had B, Z, E, D. So the first time round, we were just changing this to 5 and nobody else got changed. But now we got distance of D becomes 4. So I got to write distance of D. So everybody gets to be, I guess I use red for colors. So hang on. So we updated this to 5, infinity, infinity, infinity. That was the update. But now we go ahead and do the next one, and D is going to be 4. Distance of D equals 4. I'll write this down carefully enough. The distance of D equals 4. There it is. Distance of D equals 4. So this, I'll do it in green, has become 4. Everybody okay with that? By using C, because that's the one we popped at the top, we now get the distance is 4. We go back to the actual picture, you can see what's going on. This was 0, this was 3, and now this has got to be 6, which we had in there. And now we're doing this one, and we're going to get 5, right? We're going to go through C, and we're going to get 5. So we're doing visually, it's quite simple. All right, so that's become 5, 4. 2 plus 2 make 4. There it is, 4. So coming down here, we made it 4. There it is. So now we've got to move up. And we notice, you see, that it's going to move up. This one is going to move up that one. This is going to come down. And Z is going to go down. We get a rotation going on. D is going to move all the way to the top. And B and Z are going to rotate down. So does everybody get this? I'm going to put a check mark there. When we make D equal to 4, our heap is going to rotate. Yes? Thumbs up? You see that? We've got to we maintain the heap structure. So D is going to move up to the top. See, here's the point. D, right here, we made 4. When we made D equal to 4, it's going to move up. So what's going to give? Well, it's going to give us. Let me do an insert. So let's write this down again. So and now let's draw the picture. We're going to have D at the top. Z rotates down B rotates down once, and Z rotates down twice, and we have E over here. E is no change, but B is 5, D is 4, and Z is infinity. So that's what the heap now looks like. Everybody okay with that? And if I'm going to fill in the diagram, which I did quickly draw. So when I propage this, it will look very nice. Parent S, distance, and vertex. A, B, C, D, E, and Z. D is the one we changed the most. So D's parent became C. It hasn't been visited. Its distance is now 4. Oh, we're missing one position. Position and vertex. A, B, C, D, E, F, and Z. So rub this out. A, B, C, D. So D's move to the top. I'll do it in red. There's D. C, not been visited. The distance is 4, and its position is 1. We didn't change 0, so that's the same. Okay, A is the root. 1, 2, 3, 4, 5, 6. Somehow I've got this is not quite right. Ah. I did it right first. This is B. Then we have C, D, E. So I was right the first time. Right? D. The parent is C. The distance is 4, and the position is 1. And we didn't change that, so that's 0. So A is the root. 1, 0, minus 1. We not processing U. B is now C, 0, 5, 1. C is A, 1, 2, minus 1. Again, you're out. Then we got E is still infinity, so no parent. 0 and 0, distance infinity and infinity, and the position of E is 3, and the position of Z is 4. That got changed. So its position is 4. Its position is now changed, and B's position changed, right? There's B. B's position's changed, and its position now is 2. There we are. So there's the changes. We get some changes. All right, one more to go. And that was E, right? If we go back to the picture, we've done C, we're going to do E. So update E. Okay, so the distance to E is infinity. There it is, infinity. And let me see, going to distance to C plus the weight of C to E. The distance to C was 2. The weight of C to E, we go back up. The weight to C to E is 4. So that's going to give us 6. So that's going to give us 4 equaling 6. So we're going to set the distance of E to 6. And the parent of E to be C. So the picture is going to look like this. We're going to make E 6. So E is 6. And notice we're not going to have to make any change to our heap. So that's the only change that we're going to make. E is 6. No other changes are needed. And so that's fine. Now, if E had turned out to be 3, say, all right, so let's suppose if I backtrack, if this distance was 1, then that would make it 3. And in that case, this would be 3, and we would have to switch D and E around. In other words, we would have to change the heap. But in this particular case, no change is really necessary, just like the first case. We have D is 4, E is 6, B is 5, and we've still got Z sitting at infinity. All right. And we can draw the same thing. No change. There's actually no change. The only change that's going to happen is that E becomes 6. So E becomes 6. And E becomes 6. Hello. Distance becomes 6. Third one down is 6. Oops, do red. Its distance becomes 6. Its position doesn't change, so it's still 3. It's still 0 here, doesn't change. So in fact, that didn't change, it's still 3. And its parent is C. So we get C for E, its distance is 6, but its position stays 3. There we go. So there we are. Now we're ready, although I didn't ask you to do it. What happens if I kick out the top? So if you kick out, you would get delete min retires D. And then what you would do, so that gets kicked out. What happens, you move Z up to the top. So that gets kicked out. Z goes to the top. And then you can see B would move up. And so what you would get is B 5. E doesn't change, so that's 6. But now since B moved up, Z moved up. B moved up and Z goes down. And we end up with that picture. So when you kick out D, Z moves to the top. It's going to rotate with B, so B moves to the top and Z moves down. And now we're going to look at the neighbors of D, and if we go back to the picture, the neighbors of D would include Z, so Z gets its first value. So that's how it works. Pretty nifty. A lot of work. Not quite sure how I could ask this question, but I'll think about it. All right, any questions? All done? I will have solutions to all these quizzes up by tomorrow evening, if not earlier, so we can see it. All right, and I'll see everybody on Friday. I am trying to arrange for the TA to be available tomorrow to return old graded work. I'll send you an email tomorrow morning if I've got that up to date. Otherwise, I'll see everybody on Friday, ready to go.
Professor, would it be possible to talk to you for a few minutes just after at the end of class?
Say that again.
I would like to talk to you at the end of class.
In the class, yeah. Okay,
At the end of the session.
yeah. Apart from my TAs, can we all log out then?